Hello grade 11s, this is Physical Science and my name is Gillian. Today we are going to consolidate our knowledge of Coulomb's law, and it's all about electrostatics. So what is this electrostatics that we're talking about? Coulomb found that if we have point charges, so very small little charges that have very little mass but do have a charge, there is a force that is between them. So it can either be a force of attraction or it can be a force of repulsion. But that force is called the electrostatic force, and it is dependent on the product of the charges, so the magnitude of the charges, and it's dependent on the the square of the distance between these charges. So we're going to look at those today and how we can use that information in problems. So if you look at my board, you'll see we have already discussed a charged object and relationships, and that was Coulomb's law that we did in the big ideas lesson. So today we're going to have a look at the forces between the charges in terms of vectors, because it is a vector, and how we are going to be asked in terms of 2D problems, two-dimensional problems. So we're just going to practice today. That's all we're going to do. We're going to practice. So let's get on to our first one. And this is a lot of words, so as we are reading it, I'm going to highlight things and we're going to write into the picture what we know. So we have three small identical metal spheres, identical, and they are named P, S, and T on insulated stands. So that means that the stand has no effect on what's going on in this picture. They are initially neutral. That's interesting. So they start off as having a zero charge. So all three of them start off with a zero charge. They are then charged to carry minus 15 times 10 to the minus 9 Coulomb. Q, okay, so we don't know what that is. They haven't given it to us. And plus 2 times 10 to the minus 9 Coulomb. Okay, so there's the other charge on T. The charged spheres are brought together so that all three spheres touch each other at the same time. So these spheres are being brought together, they touch each other, and we know from our prior knowledge that if they touch each other, that nature is going to try and balance out all those charges, and so there is going to be a transfer of charge electrons from one to the other and the other to the all three of them are going to move these electrons around so that they are going to have the same charge at the end when they are taken apart. So the charge on each sphere after separation is, and there it gives us there, so that is the net charge that is going to be on our on each one of these spheres, P, S, and T. Okay, so we've got an idea of what's going on then, and we're going to move on to the first question. So it says here, determine the value of charge Q. So there we go, charge Q, what is that? So from our knowledge, we know that Q net is going to equal the charge on P plus the charge on S plus the charge on T, but there are three of them, so we divide by 3 to get the net charge. We've been told what the net charge is. Let's go back to our question and we see it is minus 3 over here, minus 3 times 10 to the minus 9, so Coulomb. So we know what that is, so minus 3 times 10 to the minus 9, and we know what the charge on P is. It is minus 15 times 10, oops, I left out a 1, 15 times 10 to the minus 9. Okay, so that's that one. plus the charge on S plus the charge on T. So I'm putting these in brackets so that when I add them together, if I've got a negative value, that's mathematically it's going to be sound, right? I need to divide all this by 3. I'm going to maneuver these values around so that I can get Q on its own, and this is what I will end up with. So Q, that's the charge on S, is going to be 3 times minus 3 times 10 to the minus 9. Oops, I put in a bracket there. Let me just erase that bracket. There we go. Back to my pen. Right, now what is going to happen underneath here? So we would have plussed this one and that one together, and then we divide the minus 3 times 10 to the minus 9 by that value, which ends up being minus 13 times 10 to the minus 9. I'm running out of space here, so I'm going to write the answer next to it. You would write it underneath it, so it's nice and neat. And the answer here for Q is plus 4 times 10 to the minus 9 Coulomb. All right, so that question is using our knowledge of when we put the charges together and they're touching, that there's going to be an evening out of the charge. Remember that you have to divide the total by the number of charges that you have in order to get the net charge. Right, our next question is, draw the electric field pattern associated with the charged spheres S and T after they have separated and returned to their original positions. Now, field patterns are patterns that show you how the force is working. Now, we don't see them unless we do some really special experiments. So what we as scientists do is we draw in those lines to give us an indication of field strength and field pattern around a charged point charge or particle. So we know that both of these S and T spheres are going to be charged the same, and they're going to be negatively charged because it's told us -3. So we have got 1 over here and we have got 1 over here, so S and T. Now, when we're drawing field lines, they are not allowed to cross. They need to go from the charge to outwards to create the pattern. So if we've got a circle, a point, then all those lines are going to move into or away from the point. So if it's a single charge, then it would be quite regular like this. Okay, so our field lines would be nice and regular, and you can see that they move from the point charge outwards. So it's like it's a radial pattern. But now we've got charges that don't like each other. They are like charges, they repel each other, and so that field line or field pattern is going to be manipulated. It's going to move. And this is how it's going to look. So I'm going to start from the inside where they interact. So you can see that the field lines, the lines themselves are showing you that there is a repulsion. Then we can fill in the rest of the lines. So you can see that they are being manipulated, they're not straight anymore, and the lines go straight from the charge outwards. Okay, and looks a bit like a spider, doesn't it? Okay, there we go. And the same applies for this other side. Now we need to indicate a direction. So when we place a very light positive charge into this field, what's going to happen to it? Well, it's going to be attracted into the negative or towards the negative charge. So that is the direction of the field. And so we need to put arrows on each single one of these lines to show the direction of the field. I'm not going to continue with that. I think you get the picture. So drawing those fields is quite important. Those rules, you need to adhere to them. Right, the spheres, each with a new charge, we know about this, are placed in different positions. So you can see the positions have now changed. S and T are perpendicular to each other. So what does that mean? It means that there is a 90 degrees angle there. And that is really important to note. It also shows us on this diagram the distance between them. So you can see the distance between S and P is 0.1 meter. The distance between P and T is 0.3 meters. What are they going to ask us? State Coulomb's law in words. So let's have a look at the equation, and from there we can work out the words. So the equation is the force, which is the electrostatic force, is equal to the constant K, Q1 times Q2 divided by the square of the distance between these charges. Okay, so let's put that into words. They haven't asked for the equation, they've asked for it in words. So we're talking about the magnitude of the electrostatic force that point charge 1, so point charge 1, represented by Q1, exerts on point charge 2, represented by Q2, that is directly proportional to the product, that's a good word, product of their magnitude of charge, and inversely proportional to the square of the distance between them. So those are the words that are really, really important. So it is the product, that word, product of the magnitude of their charge, magnitude of their charge, and so it's directly proportional to the product of the magnitude of their charge and inversely proportional to the square, that's also very important, square of the distance between them. Okay, grade 11s, that was learning work. When we come back from the break, we're going to see what else they're going to ask us in terms of vectors and how to solve those problems. Hello grade 11s, welcome back from the break. So let's dive right in. This question is now asking us calculate the magnitude, okay, there we go, magnitude, or how big the net electrostatic force is acting on sphere P. Okay, so we have two things happening here. We have S acting on P, and we've got T acting on P. So to find the net force, we're going to have to do some thinking. I like to draw a diagram first before we head into this. So I'm going to draw a diagram, that's P, okay, so that's P. Now what is happening? P is negative and S is negative. So that means that they are going to be repelling each other. So if we think about S working on P, so S is up here, P is over here, S is working on P, what is S going to be doing? Is it going to be pulling P up, or is it going to be pushing P away? Well, it's actually going to be pushing P away because the two charges are the same. They are like charges, so they will repel. So we're only looking at S working on P. And so S is going to be working in this direction. Okay, so that is the force of S working on P. Now, what about T? Well, T is also negative, and so T is also going to be pushing P away. So P is over here, T is over here. It's going to be pushing P away. It's what is T doing to P? So it is going to be pushing away. So that's that force there. And so what is our resultant force, or the net force, going to be? Well, it's going to be this one over here. Okay, there it is there. It's going to be that one there. So we can rearrange this. You know this when we go through components of vectors, components of force, we know how to do this. This is pretty straightforward for us now. So I'm going to rearrange this diagram so that that is the force of, I'm going to write here, the force of S on P. And then I'm going to transpose this, sorry, I made a mistake here. Let's just rewrite this. Let's rub this out. It's not S on P. It is actually T on P. So let's write that down. It's T on P. And then if we transpose this one down to here, then that one is going to be the force of S on P. There we go. Right, so here's our resultant. That's our net force over there. Okay. So we can see that our 90 degrees fits in there. Remember at the beginning, the question said that there was a 90 degrees. And we now need to work out these two forces in order to find the net force. The net force, we've got a 90 degrees triangle here. So the net force, we are going to use the Pythagoras Theorem to find the hypotenuse. Okay, so that's the one we want, the Pythagoras Theorem. We're going to use that one. So first of all, we have to find the force of T on P and the force of S on P. And this is how we're going to do it. We're going to use these equations that Coulomb has so generously left us. So F is equal to K, and it will be Q1, Q2 divided by R squared. Now, I'm kind of running out of time. I want to show you a different problem as well. So all I'm going to do is I'm going to substitute in really fast and then write down the answer. We don't have time to use the calculator. So this is going to be, for the first one, we need to just recognize which force it is. So I'm going to start with this one here. We're going to write S on P because that is a good way of writing it and reminding ourselves of what we're doing. So K you're going to find on the data sheet, and it is 9 times 10 to the 9. Then we pop in the values. Well, we know what they are. They are 3 times 10 to the minus 9. There are 2 of them because they are now the same. We are going to leave out the negative sign now because we're talking about the magnitude of the charges, okay, not the direction at this stage. Well, we're going to leave out the negatives. We know they're minus, and we're going to come up with a 0.1 squared. That is the distance between them, and the answer is 8,1 times 10 to the minus 6 newtons. Okay, we now need to continue to the next one. So we are going to have F of, it's now T on P, exactly the same thing. Okay, we are going to have 9 times 10 to the 9, that's the K value, and 3 times 10, I'm running out of space here. Okay, I'm going to put a square there because I'm running out of space. That's 3 times 10 to the minus 9 times 3 times 10 to the minus 9 divided by, now what is the distance? 0.3, square it. Okay, And the answer here is 9,0 times 10 to the minus 7 newtons. We are not done. We think we're done, but we're not done. Now we need to put those into the Pythagoras theorem and get an answer. So I'm going to change the color of my pen because it's getting a bit jammed here, so we can see. So what are we wanting to find? Well, we're wanting to find this net charge. Sorry, not the net charge, the net force. And so that is going to equal the square root of S on P squared plus T on P squared. Right, if we put our answers in there, so we're going to substitute in 8,1 times 10 to the minus 6 and square it, and 9,0 times 10 to the minus 7 and square it, and then we find the square root of them. Once we've added them, we get an answer of 8,15 times 10 to the minus 6 newtons. Do we have to write a direction? No. Although it is a vector and it would have direction, they are asking us for the magnitude only. So we do not need to work out the direction. If we were asked for the direction, then we would have to use a sine or cos rule to work out the degree, the direction of that vector or that force. Right, what's the next question? Calculate the very, very small increase in mass of the sphere P after it was initially charged. So we know that these spheres started off as neutral. They told us right in the beginning they start off as neutral. So what is the mass gain going to be? We're talking about electrons. Electrons are minuscule. They are extremely, extremely tiny. But the number of electrons that would have been transferred to sphere P to form its initial charge, that would give us an indication of the mass that P is going to gain. Now, we are expecting a minuscule answer here because electrons have got a really, really small mass. So how are we going to do this? Well, we have an equation. It is found in our data sheet. So the number of electrons is equal to charge divided by the charge of an electron. That makes sense, right? So this is the object or the sphere. What is its charge? We divide by the charge of an electron, and then we can get the number of electrons that have been transferred, that it's gained. So what did P initially, what was its initial charge after being neutral? It was minus 15 times 10 to the minus 9. What is the charge on an electron? So we know from our data sheet that it is minus 1,6 times 10 to the minus 19. So that's what we're going to substitute in here, minus 1,6 times 10 to the minus 19. And we then discover that this sphere P has had a number of electrons transferred to it, and that number is 9,38 times 10 to the 10 electrons. That doesn't help us with mass. Now what we've got to do is we've got to work out then the mass that sphere P has gained. So we've got the number of electrons. We also know the mass of an electron, which is really, really small. So the mass of an electron from our data sheet is 9,11 times 10, look at this, to the minus 31 kilograms. How tiny is that? So what are we going to do? Well, it's the mass gained. So we're going to say mass gained by sphere P equals the number of electrons that it's gained, obviously, times by the mass of an electron. So that is equal to, we've already worked out our answer, 9,38 times 10 to the 10. That's the number of electrons it's gained. What's the mass of a single electron? 9,11 times 10 to the minus 31. And I'm running out of space, so you're going to write this below this line. I'm going to write it next to it. And the answer is 2,85 times 10 to the minus 20 kilograms. Look at that. Tiny. Absolutely tiny. But that is the mass that is being gained by sphere P. Right, grade 11s. Unfortunately, that is all we have time for. I hope to see you in the next lesson. Ciao for now.